the screen winding up. Now it says we are live.
Not at that URL. Let me go out and click it again. Now, I still get yesterday when I click the URL from, at least from my email that I had with the invitation. I haven't actually tried it from the website. I can try that.
Let me see what's coming up on the website, Paul.
Let's see here.
I'm going to it on a separate.
Saturday, remote solar viewing. Click. Watch. Nope, it still comes up with yesterday. Unless this is a caching issue, but I've done everything I can to uncache it.
Sure as heck should not be. Okay. Let's see, what are we getting? Just a minute here. I'm going to tune in and we're going to watch and we're going to see.
All right. And we're live.
Nope, we're getting yesterday. Okay.
Refresh my page.
We got a problem, Paul, because
I'll do the same.
I went to the URL from the website and it just shows the placeholder page.
Yeah, so Jeff does.
Yeah, that was me struggling yesterday, not realizing you had to click the watch button that was down off the bottom of my screen.
yeah, I just clicked did that on my tablet and we're getting yesterday's stream.
Okay, so you're getting the same thing I am.
This stinks.
If you want to research it, I can sit here. I'll turn the volume up a bit so I'll hear you if I'm not in the room.
Okay, and meantime, we're running.
Or better still, I'll just share my desktop. So if I happen to walk away when we go live, the sun will be there.
Actually, that's not going to help because you sharing your desktop occupies my whole screen for some reason. I'm not. Well, try it again. Try it again, Paul.
Here it goes.
Okay.
Bang.
All right. That shares the desktop, but it for some reason I am not able to. Let's see. Okay, here's meeting information. Okay, we may have a meeting ID issue here. Let's see. And I'm going to have to get in touch with one of the other guys to find out if they've had any experience with this because I'm mystified.
All right, you want me to keep sharing or shut it off?
Please shut it off because I don't know how to minimize that screen to get back to studio.
I ran into the same thing. How does that work? I had the same problem. I couldn't get it off the screen. Crap, I can't remember. There aren't the usual minimize buttons.
No.
But it's in the menu somewhere in Windows. It's down along the bottom somewhere. I don't know what it is.
Well, I'm in Mac.
Yeah.
But I imagine there are similar controls available.
Mm-hmm. Is that a bass in the background or a cello?
Yeah, it's cello in the background.
Oh, do you play the cello?
Yes, I do.
Cool.
Yeah, with a bunch of other stuff.
Classical or not classical?
Yeah, I'm a classically trained musician.
Oh, I'm a self-trained folk cellist.
Oh, that's very interesting. Let me see. Who can I turn to? It sounds like an old musical.
Well, I got Adrian's phone number.
Yeah, I got Adrian's phone number too, and I'm going to ring him up right now. I don't know if he's doing anything.
He's got 15 seconds to go. Well, I know you're right. I don't think he is doing anything at 4.
That's good. Well, I hope he's answering his phone. I got him on speaker so you can hear too.
Hey, John.
Hello, Adrian.
Yes.
I brought up the Zoom meeting and put it on YouTube, and we went to stream, and we're getting, well, first of all, when I went into the Zoom controls, or rather the YouTube studio controls, and went to the videos, the video that came up as available for today was the stream from yesterday.
Oh, great.
And I tried to go to the stream for that was available, which was labeled as the stream for yesterday, and it's still what's streaming on the GLAC website is your stream from yesterday. So
Let's see. So let me look and see what the link. Let me verify that the YouTube streams, they should not be the same. I'm looking again.
did we
They are the same. He used the same page to, yeah, he put the same page to put the stream in. So what I want to do is, let's see,
this is pretty good. We crossed the streams, guys.
I knew that was a bad thing.
Yeah, we used a different stream. So what we're gonna have to do is save off yesterday's view so you can use that stream. Let me go to the general.
Yeah, now we got to put the toothpaste back in the tube.
Yeah, so what we'll do is do that. Let me.
Is that really true though? Because they're different. Here, let me look at something.
Yeah, they will be different. So, yeah, you went live with it. So,
Well, what I went live with the channel that was available because I clicked on the September 26th video, on YouTube controls, and that was your stream from yesterday.
Yeah, just use it. Go ahead and use it because you're live. So, yeah, you and Paul just go ahead and get started with it.
We can't.
No, it doesn't. It comes up with yesterday, even when we go live.
Yeah, when we went live and it came up with yesterday's stream.
Let me see that.
Are we going to different URLs? Because the URL that I get.
Same URL.
We're going to the same YouTube URL.
Yeah, I verified that they used the same YouTube URL. So what I'll do, I think what I can do is I can create a different YouTube URL and then point it at it. So let's do this. Go ahead. I'll go ahead and end this. See if I go ahead and end this stream, because I see it going.
Yeah. I
see you guys live actually.
Wait a minute. Do you see where do you see us live on YouTube?
Yeah. I'm gonna go.
That's you on YouTube.
No, I think he's going to the correct URL. We are not.
Oh, okay. So you went to the correct URL.
Well, so what I did is I went to the live stream studio.
Yeah, okay.
Where you have it starting the stream.
Yeah.
There is actually someone playing it back. Let's see.
Would it be easier, since we won't have a lot of viewers, to publish the Zoom meeting instead of YouTube?
What I think is happening is you're actually there. So what I'll do is I'll go see what happens when I go to the stream page.
Go from the Astronomy at the Beach website just to make sure you get to the same place we do.
Yeah, that's what I'll do. And what I got to do is I got to go to this Beach website, and I got to go live telescope viewing. Here we go, white light. So I click on that, and I go to watch. And this does look a lot like yesterday's.
Unless there's two of you.
Yeah.
So let's see. Yeah, so we won't. You are streaming to it, but it's not working. So what we'll do first, I'll go to chat on Aunie's thing, and I'll say be back soon. Let's see, fixing. So let's see, let me go to, all right. Go to the apps. Let's see. I'm going to type to them. So I just sent a note. Hopefully Bob gets the message. And here we go. So what I'm going to do is I'm going to end your current stream. There are people connected to this, so maybe there's a different page. Let me.
No, they're probably going there from the Astronomy at the Beach website, thinking this is today's show.
I hope not. Let's see. Let me.
But that's what they do. You know, if they click on that link, that's what they get.
Yeah.
Yeah, I need to go to some notes and see what shareable link it picked. Let's see where it went.
And I did check on the Astronomy at the Beach website. The URL for yesterday and today is different. It's not the same.
Okay, you guys are. I went to the URL it created, and you guys are all live.
Yeah, but that's not the one that's on the Astronomy at the Beach website, I bet.
Yeah, let me give this URL to Bob, because I think that'll solve it. It did create a new video or a new link.
Can I just add one thing? For everyone who's watching, if you would like to click on the like button, the thumbs up like button, please click on the thumbs up and the subscribe button so we can, it helps promote these recordings, these videos out on YouTube. So click on the thumbs up and click on the subscribe button so anything we publish new events out on these YouTube channels, you guys can be notified of the new recordings. You can check them out whenever they're available.
All right, so I told Bob what the URL is that's working.
And he's going to what? He's going to change the website?
We're going to change it on the link so that when people click on the link, they go to you and John, your faces right now. I'm actually looking at your live stream, and I'm looking at I haven't ended the stream because it's actually working. It's going to a slightly different location.
Okay.
And that's the location we're going to get people to go to.
So what you have is my shiny forehead and Paul.
And Paul on the left. Yep.
Okay.
So let me see if, all right, done. I'm going to test it now. Refresh the screen.
There we go. That worked. I just clicked on the Astronomy at the Beach website and I get us now.
Yep. So we're good to go. Fix the problem. And you guys are on and going because you did start the stream. So you're on and streaming.
Nope.
Cool.
Go to it.
Nope. You and Paul are on and streaming.
No,
Yeah.
go to the page again.
Go to the Astronomy at the Beach website, click the link for today.
You'll notice that it's working now.
It should work.
Okay. Just a minute here. I've got a.
We've put some intelligence in the chat here.
Yep, there's 2 people that are checking it out, and
Yeah, missed it.
I want to be one.
There we go. Okay.
Told you it was working.
Okay. Now, I guess, Paul, you put your screen up there now and we see the sun.
Alrighty. I was trying to put something intelligent in the chat, and I guess it doesn't take anywhere near as many characters as I typed, so I'll have to rework that. Zoom meeting, share screen. Boom. And after a certain delay, it should show up.
Well, there it is. There's Big Red.
Yeah, big orange. Behind a bunch of clouds at the
I'm
moment.
gonna jump back into Aunis,
Good.
and I've got help from Tim and Liam and Gordon, so I didn't. They're doing just fine. So you 2 carry on. I think you've got a couple
Yeah.
viewers.
Yep.
Oh, 4. You've got 4 live viewers now, probably including
Okay.
yourselves.
That's good.
And
We're good.
I will go ahead and link in this chat. Let's see. I'll go back to YouTube Studio and I'll figure that out. So you guys are all set.
Thank you. Thanks.
All right.
Bye-bye.
Yep, you're welcome.
All right. All right, Paul.
I'm still trying to pare my prepared verbiage down here to get
Well,
it. in
folks,
the
what
chat.
we have is Paul Goelz, white light solar viewing. We are looking at the sun. Paul is working on clarifying the image. And what we will see, we will see the sun in white light, which means that we will see features that appear in our spectrum, and in addition to the telescopic image, of course, the magnified image of features on the sun, which we can't see because we go blind.
Okay, I've got some stuff in chat here that explains what we're doing here. Unfortunately, the chat doesn't like my extended verbiage, so I've got to pare it down here.
Now, let's see, we've got some, okay.
Okay, this next paragraph is too long to put in chat, so I'll just speak it.
Good.
First of all, this is not live. Let me turn on the live view. Oops, it's overexposed. So let's take the gain down. That's a little bit more reasonable. Now we go live. Unfortunately, there is nothing to see other than an orange ball, because in addition to the fact we've got clouds going by, which you can see kind of in stop action on the screen, there is virtually nothing on the face of the sun today. Yesterday, there was a very faint feature that I think was eventually called a sunspot, but it is gone today, or at least I can't see it. And so if you tuned in to see something exciting on the sun, tune in next week. At the moment, we are at the very bottom of the sunspot cycle, and there isn't much going on. That means the sun is very quiet. It is not producing a lot of flares. There may be some prominences, and if you go over to the other presentation we have here at 4 o'clock, you may see something in a different wavelength. But this, as John said, is visible light. This is the same light you look at when you use your eyes. It's just filtered so it won't melt my telescope or my camera. And it gets dimmer and brighter as clouds roll by. And I look out the window, I can see shadows, but they're not real crisp shadows.
Yes,
So,
and unfortunately, astronomy has not come up with a cloud filter yet. But if Paul, if we were seeing a sunspot, those little black dots that show up on the sun, and they're very, very clear, what would we be looking at? What is a sunspot?
a sunspot is a cooler area, relatively speaking. They're still pretty hot. The surface of the sun is what, around 10,000 degrees? Sunspots might be 7,000. So although that's still incredibly hot, it is that much cooler than the rest of the surface, so it looks much darker. It would still, of course, be extremely bright if that's all you were looking at. But that is what is a sunspot. They're composed of magnetic features. I just did some reading this morning about what goes on inside the sun and how long it takes that energy to get out. And what we're seeing is the very surface of the sun. And I should take that back. It is not actually a surface. The sun does not have a surface. What we see has a boundary, but the sun is really just a great big ball of gas. Let me put something on the screen here, if it'll cooperate, which will show what the sun might look like in 3 or 4 or 5 years. Okay, that's just a photograph, but that is what the sun might look like in 3 or 4 years when it's more active. These are very large sunspots aimed directly at us. So whenever that photograph was taken, things might have been pretty interesting on the Earth. But as opposed to that, this is what we have today. And
well, let's talk a little bit about the sun then. The sun composes, of all the matter in our solar system, from the sun all the way out into the Kuiper Belt objects, Pluto and Oumuamua, and those whatever those other objects are named, I don't remember them all. But the sun composes 99 and 86/100% of all of the mass in the solar system.
Yes, that's a fascinating statistic. I just read that this morning. I didn't realize how.
Yeah, in other words, the solar system is the sun and just a little bit of dust that's orbiting around it. And that kind of explains, if you go back to your Newtonian physics, that kind of explains why how we have these vast orbits. Jupiter out there, the largest planet at 500 million miles, still under the gravitational influence of the sun, and then Saturn, the next largest of the planets, out there at 800 million miles, almost, a couple 100 million miles short of a billion. And then the other gas giants, Uranus and Neptune. The sun's the big thing. The sun is what the solar system is all about. And of course, Copernicus helped relieve us of our self-centered attitude about us. The history of things in astronomy is You know, astronomy is the oldest science because people have always been able to see the sky. And then, of course, I'm sure that some people before Aristotle realized that the Earth was round, but Aristotle was the one who clarified it. He said, of course, the Earth is round. Look at a lunar eclipse. The shadow of the Earth is an arc, is circular. So, by all means, of course, the Earth is round. And then Copernicus established that the sun was the center of the solar system. And then Kepler, Johannes Kepler, worked out the orbits of the planets, and then science proceeded from there. But the sun is an amazing thing. A star is an amazing thing. Another interesting datum about the sun is that, of course, science didn't know what created the heat in the sun. What is this thing? It's hot. We know that it's hot because we receive the Earth receives. The Earth only gets about 2/1000 of the radiation that the sun radiates. We're way out there, 93 million miles away, and we just get that little bit of that albedo. And of course, that we didn't know what created the heat, the energy of the sun until Hans Bethe around in the 1930s, I think it was later in the 30s, actually worked out what makes the heat in the sun, the proton-proton process that creates energy. And we think of that as fusion, nuclear fusion. Two protons under tremendous heat and tremendous pressure actually combine. And then if you look up the process, the proton-proton process in Wikipedia, there's an excellent picture of it there, a graphic, showing what creates the energy. And this process goes on at what would be the center of the sun, this gas ball. And here's another interesting and mind-boggling figure. The sun fuses 168 million tons of hydrogen every second. Now, I didn't come up with that. That's, far greater minds than mine came up with that. That's a huge, you think, well, how can that go on forever and ever like it seems to have done? But 168 million tons of hydrogen at the center of the sun might not even be, bigger than the end of your little finger. And that's how it can fuse. So that's what creates the energy in the sun. And before Hans Bethe worked out that nucleosynthesis process, people just guessed at what created the why the sun was hot. It's a big mystery. And now, okay, so the sun creates light too, sunlight. I mean, that's the heat and the light. Those are the important things that the sun does for us. That's why there's life on Earth. And so we know it makes the heat, and it also makes the light. Photons get released or produced by that proton-proton nucleosynthesis. And that proton starts at the center of the sun. Well, the sun's, the diameter of the sun is about 864,000 miles, about 13,000, or 1,300,000 kilometers, something like that. It's a big guy. That photon that's created at the center of the sun, when those protons are fused, that proton starts a journey through the sun. Now, I'm going to give you to get an idea of how dense the sun is, how compact, how full of mass and energy it is, the photon that is created at the center of the sun can take, and these are scientific estimates, takes between 10,000 and 40,000 years to get from the center of the sun to the surface. And again, that's a corker. I mean, that's a doozy there. That's I'm still working with that one.
Yeah, I read that this morning. I'm still wrapping my head around it.
Yes. Well, this is physics. This is something that's so much fun about physics. And really, this is one of the things that really inspires a lot of people, a lot of students to learn physics, because how can that be? You know, how, well, let's find out. And, you know, the curious mind is what moves us forward. But we started out talking about sunspots, what a sunspot is. And thinking about this tremendous amount of energy created at the sun, this tremendous mass, and these photons and this energy traveling from the center of the sun to the outer boundary of the sun. What a sunspot is when that energy gets all knotted up. And it's a good metaphor for a sunspot is if you take strands of a rope and tie them in a bunch of knots. That's what's happening to the energy in the sun. It's so extraordinarily turbulent that this energy gets knotted up, and because of some of the energy is consumed in this process of this commotion, that sunspot area is a little bit cooler than the other boundary areas that we see on the sun. The sun is just absolutely amazing. Reading about the sun will amaze you. Reading about the history of man's knowledge of the sun and the history of discoveries about it, and then the way the sun and stars affect their surroundings is amazing.
The other thing that you tend to forget is the sun makes everything go, literally. All of our energy. Is there any energy here on the earth that did not originally come from the sun? Like even radioactive elements came from the sun, didn't they?
All of the elements except hydrogen originated in stars. The sun, that proton process creates helium. Helium is one of the products of the proton process, and then the other light elements are also products of the nucleosynthesis. There is another in very much larger stars that have burnt off a lot of their hydrogen. There is another process, the carbon, nitrogen, oxygen cycle, that is another type of nuclear synthesis that also creates energy. And this process of the element, creating elements through nucleosynthesis goes on right up to iron, because these elements through nucleosynthesis can create, through fusion, can create energy right up to the element of iron. And at that point, when you get to iron, then there's no more nucleosynthesis that takes place, because it takes more energy to fuse iron than it would be released by the fusion process. So all the elements beyond iron are created in some other way. and it's thought that those elements are created by other very energetic processes in the universe, such as supernova, and that's I think that's the prevailing theory right now, is that the heavier elements largely are created in very highly energetic processes that have to do with what we could regard as destructive, or, well, it's hard to say destructive, because the old rule, matter can be neither created nor destroyed, but can change from one form to another. Of course, we know from Einstein or from Hans Bethe that matter can change into energy, E equals mc squared, and that's another exciting thing about physics, is getting into that the theory of energy and matter. But all of the elements are, hydrogen was it. We think, we're fairly certain that hydrogen was about it, and that's a proton, proton and an electron, and that was it from the beginning. And then everything was created from that proton and that electron that was the original stuff of the universe, of the Big Bang. And if you look at the proton-proton process, you'll see how neutrons are created, how neutrons develop in the proton-proton process. It's a lot to hold on to. Hey, there's the sun again, Paul.
Yeah, well, such as it is, should remind anybody just tuning in that what you're seeing is the image of the sun through clouds. The features that you see going across the sun are clouds. They're not happening on the sun. And it's probably more interesting than the sun would be if there weren't clouds, because there is nothing on the sun today.
No sunspots.
No sunspots, no structures, no nothing. There was a very faint area that I think turned into a sunspot briefly as of this morning, according to science weather, that is, to my eyes, gone. So the sun is totally blank. So if those clouds went away, you'd see an orange ball, and that's it. I put most of it in the chat section, but I should describe briefly for anybody who's interested how this image is coming to you. This is a Meade 8-inch telescope out in my driveway, following the sun, and it's using a glass solar filter. It goes through the image train. The camera is an astronomical camera. It also has a UV and infrared blocking filter just for good measure, also for a sharper image. And that all comes into the house over an Ethernet cable, and I broadcast it, and it ends up on YouTube. I can also use that same setup at night to point to objects and to image them in the comfort of the house. I haven't done this in the winter yet, but I'm sure it will be very welcome in the winter to be able to set it up, align it, walk in the house, and be warm, unlike my equipment sitting out in the driveway. We should also point out that there is another presentation going on at the same time. If you go back to the Astronomy at the Beach website and look for the other solar presentation, he is imaging the sun in a different wavelength. I'm using regular visible light, but the other presentation is using hydrogen alpha light, which is a very narrow band of wavelengths emitted by hydrogen alpha. And restricting your image to that wavelength means you can now see prominences and some structure on the sun that are not visible in my view. looks like at the moment, nothing's visible in my view. Big old cloud just went by. And it looks like that might be close to the end of the sun because I don't see any breaks in the clouds to the west of where I am. Yeah, what does it look like out where you are? I can turn the gain up, see what we can get through the clouds, but probably not much. No, that's pretty dark. Oh, no, it isn't because I put in the wrong number. Let's do this again. Yeah, we get something.
Well, now, here's something interesting. Why can't we see through the clouds? They're just water. And if you...
Wrong wavelength.
wrong? Well, yeah, but you can look right through a glass of water. I mean, you can see right through it, right? You can see
yes.
on a look, go up fishing in those Canadian lakes, and you can see to the bottom of the lake there. The problem is that that water is a 3-atom molecule, H2O, and when you get a lot of it, when you get an awful lot of it, it really reflects light. Now that, we're not seeing the sun, but the sun is being reflected from the top of the clouds. And here's a little lesson about the carbon dioxide in our atmosphere also. Carbon dioxide is also a 3-atom molecule that reflects energy, reflects light, UV, ultraviolet. When the clouds go over, you're not going to get as good a tan. You don't sit out in a cloud under a cloudy sky to get a tan because you don't get that UV. Well, same thing happens with carbon dioxide in the atmosphere. It reflects the sunlight back, away from the earth. That's why when the clouds go over, immediately you can feel kind of a cooling effect. Well, the same thing happens from the earth. The earth also reflects, some heat outwards. And if there's a lot of carbon dioxide in the atmosphere, that's going to reflect that heat back to us. And that is the fact of climate change. The vast increase in the 3-atom molecules in our atmosphere reflecting heat back to the earth. It is a physical and chemical fact that happens. And there is twice as much carbon dioxide in our atmosphere today than there was at the time of the presidency of Thomas Jefferson. And that definitely has an effect on the heating of the planet. The position of the sun relative to the earth has changed only microscopically since that time. And it's true that, over time, the orbit of the earth around the sun changes very slightly. And over time, the angle of the earth, there are 23-degree angle to our orbit around the sun, that also will change. That won't create a vastly significant difference in total global temperature. So learn about carbon dioxide. If you look at Venus, the order of brightness of objects in the sky, of course, the sun is first. Then the moon is the next brightest. The next brightest natural object in the sky is Venus. Silvery, like a mirror. And Venus has a heavily carbon dioxide atmosphere, and it's like a mirror. So that's what, carbon dioxide is a mirror for heat and light. So that's a little bit about that. Form your own conclusions. Those are the facts as I know them. Always check me out. But that's a little bit about sunlight. And let's see, where do we Oh, we started talking about this when the sun was clouded, and now we see it.
It's still pretty clouded, actually, although I can
Okay.
see shadows on the ground outside.
Okay, but you turned up the gain.
I've been running the gain up and down as the sun gets brighter and dimmer,
Mhm.
or I
So you
should
have a
say,
lot
as
of gain
clouds
on
go
there
in
right
front of
now.
it. Yeah, as clouds go past the sun.
Okay, so if the clouds pass the sun, this would be like the light from a flashlight on our screen, right?
Yes, yes, and I have the gain 10 times what it is if the sun is completely unobscured. So this this may look fairly clean, but there's still considerable cloud cover between my telescope and the sun. There you can see it rolling through again.
Yeah, yeah. I see the clouds obscuring the sun.
It's too bad. A couple months ago, I had it out looking at the sun, and there was a nice little sunspot group. It's too bad we can't show anything today.
Well, that's an interesting thing, Paul, because I have a pair of solar binoculars. They're white light, binoculars.
Hmm.
Coronado. They're 10 power, 10 by 20. Kind of look like compact binoculars. And I'm retired now, but when I was working, I got off work about 3 o'clock in the afternoon, and every day I would go out when it was not cloudy, and I would look at the sun for sunspots. And this was several years ago when we still had some sunspots. And every day I would keep track of the sunspots because the sun rotates. It takes about 28 days
Yeah,
uh,
about that.
at the equator for the sun to make one rotation. And so from day to day, I would see those sunspots move around the sun, and I would see perhaps some new sunspots. So it was fun to watch the sunspots, see what was going on the surface. There's an archive.
I'm preparing a couple photos here since there's nothing exciting happening on the sun. Here are a couple shots from, let's see, looks like this was December, Christmas actually, in 2000, if my date stamp is right. And this is the sun uh, during a partial eclipse. You make that a little bit bigger.
Okay. Yeah, there's a lot going on there.
Yeah, you got some sunspots again. This appears to be actually I'm well it says it was captured in 2000. My file is dated 2018, so now I'm not really sure. But this is a partial eclipse from here from Michigan. We've got 1, 2, 3, 4, 5, 6 easily visible sunspots, and then just the beginning of the eclipse here.
Yeah.
And,
Well, now let's do a little arithmetic here, Paul.
yeah, what would the sunspot number be? I forget what the formula is.
Um,
1, 2, 3, 4, 5. There might be a sixth one there. Call it 7.
well, I'm just thinking about the solar minima and solar maxima, which we haven't
And
talked about.
I'm pretty sure that was 2000 because this looks to me like a video capture, and I wasn't doing video captures in 2018. So I think this date is correct.
Yeah. Yeah, and the sun, the sun cycle is what, 11 to 12 years.
Yeah.
So thinking back, let's see. Okay, we entered a solar minimum when 2016 or 2017.
Well, we're just coming out of it in 2020, so I think 2019 might have been the absolute bottom.
Okay, so if we count back from that, then if 2019 is the bottom, then
I think that's 2 cycles.
yeah. Anyway, this would be right around the middle of a solar cycle.
Mm-hmm.
And the solar cycle is actually is kind of the sunspot cycle, and there is a slight variation in what we regard as the temperature of the sun, and the temperature of the sun is can be thought of in many different ways. The surface temperature of the sun, as you said, Paul, is is around 10,000 Fahrenheit.
Yeah, out here where there's not sunspots, that's probably about 10,000.
Yeah, and yet the solar corona is
Hotter.
well, it's millions of degrees.
Yeah.
However, the solar corona is formed of a dispersed gas. It has nowhere near the density of the what we would call as the boundary, the visible boundary layer of our sun. And you know, how can a very dispersed gas be that hot? Well, you have to remember that heat is a measure of the motion of a particle, of a molecule, or an atom. And the corona of the sun, those particles in the corona of the sun are extremely energetic. And that's something that's still being worked on. And I'm way behind the curve on my solar corona theory. But it is millions of degrees out in the corona, which is nowhere near the density of the sun. The solar corona is what you saw if you looked at the 2017 eclipse, and when the sun was completely covered by the moon, that bright area around the sun was the corona. And that's what we can't see in daylight, but it is remarkable during a solar eclipse. And we have a solar eclipse coming up 2024.
Something like that.
I think it is. And it's going to be very close to us. The path of the eclipse is going through Ohio, west central Ohio. It's coming up through Texas, I believe, and then will come through Ohio. So by just traveling maybe less than 100 miles, you could be in an area where you could be under totality, which is a remarkable thing. If you have the chance to do it, definitely take the opportunity, because it is for most people, it's a once in a lifetime experience.
I'm pulling up, here it is. Let's see here. Slide this over here. This is, I guess I can't easily make that bigger. Here is the path of the April 8th, 2024 eclipse. So we don't have to go too far down into Ohio.
Not at all. Sandusky, in the area of through around Sandusky,
yeah,
is convenient. Yeah.
And I must say, I've never seen one. I've never seen a total eclipse.
Well, I was out in Nebraska, right directly under totality in 2017, and it is remarkable, and it's a lot of fun. And if you're in an area, in a park or some place that's opened itself up for viewing, you know, high school football and baseball fields, public parks and like that, there'll be a crowd there, and it'll be a lot of fun. Get yourself equipped, get your eclipse glasses, study up, and just be ready for it, because
and probably write down a schedule of exactly what you want to do, because you've only got, what, 3 or 4 minutes?
Yeah, be prepared, because the totality will, I think, in this in that area of Ohio, totality will be a little bit less than 2 minutes, or right around maybe a little bit less than 3 minutes.
Yeah, so you need an agenda.
Yeah. And I can guarantee you, when that sun reaches, when the eclipse reaches totality, and when that corona flares out, there's going to be a real whoop from the crowd. Everyone's going to go, "Oh!" It's it's irresistible.
So in case anybody missed it, that's April 8th in 2024. Look it up, decide where you're going to be, probably decide how you're going to get there, find 2 or 3 alternate spots in case it's cloudy where you are.
And plan to be someplace where parking will be available, and where you can be out in a field, you know,
Yeah.
with plenty of horizon. and then read up on it. There will be tons of articles, the news ahead of it, and so forth. But don't miss it if you have the opportunity to see it. It is I can't I can't express in sufficient words how remarkable the experience is.
And find a friend that has an airplane. That would be the best way. Because by definition, airports are nice flat spaces and you can easily get from one to another to dodge the weather. This
Yeah.
might be the only chance to see one without a huge trip.
Yeah.
Well, again, for anybody who's tuned in, looks like we have 10 watching at the moment. This is our sun in visible light. This is the way it would look if you could look at it directly and not ruin your eyes. Because the sun has a regular 11-year cycle where it goes from being very active and producing sunspots and flares and activity to being very quiet. We're at just a little bit past the minimum right now. So the sun is very quiet and there is nothing to see on the sun. You can look at it, you can say, oh, I saw that, but there's nothing. If I zoom in, I don't know whether the YouTube stream is high enough resolution to see it. There is a little bit of granulation that you can see here. Probably what you see on YouTube is fake due to compression artifacts, but there is some granulation here, but there is absolutely no detail. There's nothing going on anywhere. Yesterday, there was something over here, and it probably rotated to maybe around this area today. And if I use my imagination, I can see there might be a slightly different brightness area right there. But for all intents and purposes, there is nothing there. So use this image as comparison, and then go back to the Astronomy at the Beach website and flip over to the hydrogen alpha view that one of our other people is showing. In hydrogen alpha, which is a very narrow specific wavelength that eliminates most of the other energy that you're seeing here, you can see prominences and things going along the edge. You will see more structure here on the inside because you're only looking at one very specific wavelength. This is a very broadband view, and the sun is so energetic it hides any of the finer details. There is actually a lot going on out here where it's black, but it is much, much less bright than the sun. So if I expose for the sun, I don't see it out here. If I expose for out here, the camera blows up. The sun is far too bright to be able to see anything that is significantly less bright than the sun itself without taking special precautions. There are solar cameras that have a physical disk that will block the sun. The trouble is they don't work very well down here on Earth because we have the atmosphere and the clouds that are scattering light. So that still ruins the view around the sun. It works better in space.
Yeah, and Paul, I've looked over at Ani's site, and he is searching for little significances with his, with the hydrogen alpha view. He can pick out some very, very small, faint things, but we're not getting any of the big, exciting sunspots, prominences, and so forth. That,
oh, really? He had a couple prominences yesterday, as I remember.
Yes, yes.
Maybe they've dissipated.
And that's another very interesting thing. I look at the sun. I have a what's called a PST, a personal solar telescope that views in the hydrogen alpha spectrum, and watching prominences on the sun, these flares that you can see protruding from the circumference of the boundary of the mass of the sun, And watching them, they're just they very slowly proceed out from the surface in these what become these great arcs, because this is energy and mass that is being that is kind of launching itself away from the sun and then being pulled back because of the tremendous gravity of the sun. And
Can you see any movement in real time?
pardon?
Can you see movement in real time?
Well, if real time is a period of hours,
Yeah.
you can see movement, but again, the sun is 864,000 miles in diameter. So if you see something poking out from the side of it, it's thousands of miles, and these flares and these ejecta, they're moving at thousands of miles an hour, and you can barely see them progress over hours of time because the sun is so big. And what really happens often is because the sun, again, is rotating on that about 28.6 day cycle at the equator, you actually can see the sun rotate actually a little more than you see the motion of the flare.
Mm-hmm.
It's fun to watch. It is fun to watch.
And for comparison's sake, if I move my mouse pointer here onto the sun, the Earth is what? Not quite as big as the head of that arrow.
That's about it.
Yeah, just for comparison's sake, just to keep this whole thing in scale, the Earth would probably fit inside the arrow of my mouse pointer.
Yes. Oh, the sun is 333,000 times the mass of the Earth. And you have to consider the Earth is most massive at its core. We're not the massive part of the Earth. We're the dust on the surface. So a lot there, a lot going on there.
I still keep coming back to the fact that the sun makes everything go. All of our energy comes from the sun. Plant life, fossil energy, everything we use originated with the sun. Without the sun, we would have no Earth, we would have no solar system, we would have no energy, we would have nothing. We wouldn't exist.
True. Well, we wouldn't even be here because the accretion, the formation of stars involves very, very slow, over tens of millions of years, the gravitational attraction of matter in the galaxy. Last night, Don Swetzik was showing the pillars of creation, famous photograph from the Hubble, an area of a lot of hydrogen and dust in the galaxy, where stars are being formed. And of course, the star is formed almost exclusively of hydrogen, which is the most abundant element in the universe. And then, of course, dust does, attract around it and form kind of accretes around it, and then that dust becomes, more compacted by the gravitational effect of the growing star, and the dust forms into the planets. Now, and that's an interesting subject too. That's an entirely another topic, but it all starts with the sun forming from the hydrogen.
It's a good discussion though, because again, the sun is the center of it all. And it's amazing that we can look at it. It's amazing that we can look at what is in effect a continuous hydrogen fusion reaction.
Yes, yeah.
The,
Well,
the
by the way,
best we can do here is a big bang, but the sun's
Yeah.
been doing it for 4 billion years.
Yes, yeah. It's basically a hydrogen bomb inside there that is just a going off all the time and creating this huge amount of energy. And that number that I gave out, the 168 million tons of hydrogen fusing every second, all of that hydrogen isn't completely consumed, because in the process, some protons are also the product of that process. So the sun actually, in a way, recycles hydrogen to use it over and over again, or the proton matter. We can't say hydrogen because they're just protons. A molecule of hydrogen, of course, is a proton and an electron. But at the heat and the density at the core of the sun, the electrons are stripped from the protons. And actually, through the process, kind of get remade. It's interesting. Like I said, look at a chart, a graphic depiction, drawing of the proton process. It's fascinating, and it's quite understandable. You learn a little bit about those subatomic particles. You know, a positron, a gamma ray, a neutrino. These different things, some of the kind of basic components of mass and energy. And the proton process is a good way to start learning about nuclear physics.
How about we take a short break here and let me put up a couple pictures. Again, since there's nothing really to see on the sun, here is a couple pictures of what I'm using to bring you that picture of nothingness. This is a Meade 8-inch reflecting telescope sitting on a mount on a tripod. This is a guide scope for when I do photography at night, but this is not being used today because it's far too sensitive. So it has a lens cap and some tinfoil over it just to make sure it doesn't get hurt. This object right here is a motorized focuser. So inside the house, I can refocus the image if I need to. And then this red object is the camera. This is a specialized astronomical camera that has a cooled sensor. And you cool a sensor because the colder it gets, the less noise it produces. So when I cool a sensor down to maybe 20 degrees, 30 degrees below ambient, it is much less noisy, and I can make cleaner images, which is useful in my location because this is a very light polluted location. So the less noise I end up with before I start processing, the better. Here's another close-up showing the telescope. This is actually a focal reducer that makes the view a little bit wider and brighter. Focuser again, here's the camera. And from the side. Just for the techies in the audience, if there are any, this is what this setup looks like. It looks complicated. It's got all kinds of wires because most of these telescopes were never designed to allow you to route all your wires so they don't get tangled up in things. So I've spent quite a bit of time trying to figure out how to route those wires so when I move the telescope remotely, they don't get all tangled up. But that's what it takes to get this miserable image to you. Let's turn the gain back up here. Get that a little bit brighter. Yeah, that's a little better. And let's see, looking out the window, it looks like it's pretty solid overcast. So it may get brighter and dimmer, but it isn't going to get really good today.
Yeah, it'd be a great day to be out fishing, I think, or something like that.
Yeah, or doing something other than trying to take a photograph up.
Trying to look at the sun. Yeah.
But again, this is a point of comparison. This is what it looks like in visible light. And we have another presentation going on another channel that you can get to from the Astronomy at the Beach website that is showing the sun in a different wavelength that will reveal more detail if there is detail to reveal.
Well, Ani's not having much luck over there.
He's not having much luck either. Okay.
He's got pretty much the same issue that you have.
Tell him we sympathize.
Well,
and we really sympathize with the people tonight.
yeah, they're going to be looking at some pictures tonight, I think. Although there could be some, it was what we in the amateur astronomy business call sucker hole astronomy.
Yeah.
And that's when you kind of look between the clouds and catch what you can.
Actually, it was interesting last night. It looked clear, and it actually was clear, but I was trying to do some imaging. I was following along with one of the virtual viewing sessions, imaging the same things, and his skies were a lot clearer than mine. And it was actually amazing how awful the skies were. I went outside at one point and I looked, and I could literally not find the Big Dipper. I could see Arcturus, but Arcturus was a really dim star. And there was, seems to me I could see Vega straight up, but other than that, the skies were truly awful last night, and they look like they're going to be worse tonight.
Well, and the particulate matter in the sky is not helping because the fires.
That and the humidity.
Yeah, the humidity, and then the fires on the West Coast in Washington, Oregon, and California have created a tremendous amount of particulate matter, fine particulate matter ash, that is actually enters the jet stream and crosses the country, completely across the country. A couple of years ago, we had the same issue with forest fires in Alberta, Canada, which really interfered with the clarity of our views. We could still see stars, but it was like looking through a little bit of a fog. And it was interesting because last night there was one viewer on the nighttime viewing, the live viewing, who said her father was an airplane pilot. And that he said that being up, several miles up, he could notice, and the weather people commented on dust all the way to Baltimore.
Wow.
So we're still being affected by that dust. And if you don't think dust interferes or dust is prominent, get a look at the Milky Way, because that's that's dust. Very, very, very fine dust within our galaxy, and that's an interesting thing also, because the sun, of course, we see light and heat from the sun, but there's also a solar wind, and the solar wind is actually the photons, the energy of the photons that are being emitted by the sun. Photons, of course, photons travel at the speed of light. Gosh, who'd have thunk it?
Yeah.
And but they photons don't stop. They just keep on going until they're interfered with something, because they have virtually no mass, and they just keep going. And that's why we can see, we can see light from galaxies that are, hundreds of billions of light years away from us. And a light year is 5,800,000,000,000 miles. It's an unimaginable distance. It's the amount of distance that light travels in 1 year. Well, this light, actually, this solar wind, the light does have a very, very small amount of energy, but there's an awful lot of it out there. And you have little dust particles out, very, very thinly distributed in the galaxy. These dust particles actually get impacted by the photons. And if you ever seen one of these little items that looks like a light bulb with a little fan inside of it?
I have one on the kitchen windowsill.
And I can never remember the proper name of it. It's But
Photo something or other.
yeah, it's a great toy.
Mhm.
And what it is it's a little fan inside a vacuum bulb, and one side is black and the other side is silver. Of each one of these veins in this thing, and it spins because of the action of photons. Because the photons obviously can travel through the glass, but they have an impact on everything. And because of the differential absorption qualities of the veins on this little fan, one side black and the other side being highly reflective. And of course, black absorbs light, and the silver reflects light. And there is a common misconception about how these things work. So I recommend looking it up to see for sure. But photons have energy and they can make things move. So this dust out in space, and a dust particle, if you look at it microscopically, it's not perfectly round. It has little edges on it and so forth. And the photons hit the dust particles. And over millions and millions of years, because one side of the dust particle is going to be more receptive to being hit by the photons than another side, these dust particles start spinning. And the photons, over millions of years, increase their rate of spin. And they get up, even a little tiny dust particle gets up to such a very high rate of spin that it flies apart. And of course creates more dust particles. And over millions and millions of years, those dust particles, impacted by photons, they spin. And again, over the millions of years, the rate of spin increases, and those dust particles fly apart. So the dust in space, the dust in the Milky Way that we see, is extremely fine, finer than the dust on Earth. The dust that we speak of. It's just another fascinating thing about the physics of the galaxy and the physics of stars and the energy that they create. Physics and astronomy is full of fun trivia like that.
Well, there's also some interesting things to think about when you think about what is going to happen when our star runs out of fuel. It's been going for what, 4 billion years? It'll go for maybe another 4, but there will be an end. And
Yes.
that end is not going to be pretty for us.
No, it's, and then again, now we're thinking, and we're kind of conflating cosmic time with anthropological time. To think that human beings will still exist in the form that we are in several billion years, it kind of defies what we know about organisms. So, perhaps by that time we'll be some other form of life, or we'll be like, the pincushions on the Muppets, a liquid in a jar that exists entirely intellectually, or something like that. Again, cosmic time and anthropological time are vastly different.
But when it does run out of fuel,
Yeah,
what we think will happen is it will start to expand.
Yeah.
And it will get bigger and bigger until it gets to at least the orbit of Venus, maybe even more. And then at some point it can't support that, so it collapses and blows off all of that outer shell. And then it turns into a white dwarf. And I'm looking here to see, I have a photo of a couple examples of that. Here's my favorite. It's just a pretty image as well as being an example of what happens when a star dies. This is the Dumbbell Nebula.
Oh, that's great.
And this right here in the center is the star that started it all. You know, that could be our sun at some point. And what's this thing across? 4, 5, 6, 7 light years, perhaps?
Yeah, it's several light years, at
It,
least.
it's huge.
Yeah.
So that's what our solar system will look like at some point. And like you said, we probably won't be around in this form to be here. Hopefully we will have, A, not blown each other up, and B, figured out some way to leave.
Yeah, and get far away. Actually, get probably in the neighborhood of another star that has a habitable planet system, because nothing in the solar system will, you know, unless we, you know, figure out a way to make heat that would replace the sun, make energy that would replace the energy of the sun, it would be difficult. One thing about the life of the star, like you said, Paul, the star will blow off its outer layers, will burn up its outer layers. The fuel inside will fuse again up to iron, and it will be largely a ball of hot iron, very hot, white hot. That's why it's called a white dwarf. It will become much smaller, and let's think about the ice skater pulling her arms in or his arms in and spinning faster. Well, when the rotational momentum is conserved, and so it will spin faster. It'll be this white hot ball of largely of iron and lesser elements, extremely dense, much smaller. I forget how much smaller they say it will be, but you know, much closer to the size, actually closer to the size of one of the planets. And it will continue to cool because it will no longer be fusing particles to make energy. And there are other white dwarfs in the galaxy, of course, in our galaxy. A lot of them have been spotted. And the white dwarfs, those are stars that burned up their hydrogen and their helium and burned everything up all the way to iron. And now they're just cooling off.
Well, there's a star currently that is going through that people have been watching pretty intently. I never know how to pronounce it. Is it Betelgeuse?
Betelgeuse.
Betelgeuse is in the red giant phase right now. And there have been a couple times recently where astronomers thought that perhaps it was about to go supernova, and it disappointed them. But at some point, not too long from now, in cosmological terms, it will. And it will be quite spectacular from Earth. Actually, it may already have happened. We just don't know it yet.
Well, yeah, I think Betelgeuse is out there about 400 light years.
Yeah, so if it happened any time up to the last 400 years, we just haven't seen it yet.
Yeah.
Fortunately, we're far enough away
Yeah.
that it won't affect us.
I should look at distance. Distance of objects in space is they're relatively approximate, but we know that Betelgeuse is way out there, and I may be confusing it with an Antares, which is an even larger star, but it's out there, you know, dozens of light years at least. Now our sun will not go supernova like Betelgeuse, which is a red giant, because our sun, the mass of our sun is less than what's called, and here's a big one, the Chandrasekhar limit, which is about 1.4 times the mass of the sun. And so our sun isn't quite big enough to go supernova, but it will expand, vastly expand. and burn off its the remaining gases and become this white dwarf, and then continue to cool, and eventually will become a black dwarf. And we know of no black dwarfs anywhere in the universe because it's not
Because
thought
they're
that
black.
well, it's also not thought that the universe has been around long enough for
For
any
them to
star to
cool off.
become a black dwarf, because they say it will take perhaps 15 billion years, or at least for our sun another 10 to 12 billion years before it would get anywhere close to that. So even the universe will be changing over time, of course.
Yeah, I just looked it up. It's about 700 light years from us, we think. And they're thinking it's going to go supernova within the next 100,000 years. So watch it every night. You may see something.
That's right. And if it does go supernova, you'll have several days and nights to see it, because at the distance that it is, it very likely would be visible in daylight.
Or even through clouds.
Gosh, that'd be great. Give us something to look at. That's actually quite good, Paul, that you know using a lot of gain. If there were features on the sun, we would be able to see them.
Yes, if they were big enough, you'd be able to see it right through all of the clouds and the muck that's in front of it. It's I'm looking outside and there are shadows, but they're faint. So the sun is pretty obscured. I just have the gain cranked up. Let me just briefly here put it down to what it should be. This is about what I use when it is not clouded over. And
Yeah.
by comparison, that's what it is. So turn the gain up again. Oops, a little too far. Yeah, we'll call that good. Notice how indistinct it is around the edge here. That's because of all the refraction happening in the clouds.
Yeah.
This would normally be nice and crisp.
Yes, and we can actually see we see some clouds affecting the brightness now. You know, a little word about technology. 20 years ago, when or so ago, when I first got into this, when my daughter got me active in astronomy, we would not have had this opportunity. We didn't have the equipment.
Didn't have the internet.
We have today to do this. I mean, the opportunities and the availability of observation is so much greater. The equipment is it's I wouldn't say it's inexpensive, but I would say that it is surprisingly affordable for what it does, and it's if you can operate if you're at all computer savvy, and know a little bit about DC wiring, and you learn that, these things are really available and fun to do. And now there are telescopes that can be purchased that are dedicated astrographs that are dedicated to doing this kind of observing with these what are called charge coupled devices, which is basically your digital camera.
I should add to that easy and fun usually, but I'm a retired engineer and I have found this to be extremely frustrating to get all this stuff to actually work together. You have people writing various pieces of software. They don't communicate with each other. They don't support it very well. The documentation is terrible. So it's been a trial and error effort for me over the last 2, 3, 4 weeks to actually get this all so that I could bring this image to you and have it work reliably.
Well, and yes, that is true. That I learned. I don't do digital viewing. I'm an eyepiece guy, and public events and like that. But I really appreciate all of this that's available to all of us. And I learned a new term last night, Paul, dithering.
Yes.
I didn't know that that dithering could be such a challenge.
Well, my software will do it automatically, and I don't use it yet. But yes, dithering is what you do to spread out some artifacts that might be due to your camera and spread them out so they're semi-random and they're not as noticeable. So if I take a whole series of images and then I put them together into a final image, what you do is you move the image very slightly from one frame to the next. So if you have like a pattern across the image from your imager, or if you have hot or cold pixels, it spreads them out and makes them into random noise that your eye doesn't pick up. Your eye is very good at seeing regular patterns.
And yet, as a child, I was cautioned against the dithering.
Yes.
It was a pejorative term, and now it's productive. How things change.
The other thing that electronic astronomy does that is actually what got me back into it. The telescope you saw in those pictures, I bought 25 years ago. And that was before CCD cameras were anything like they are today. They existed, they were either grossly expensive, or the one that I eventually bought it functioned, but it had an imager that had 256 pixels by 256 pixels.
Yep.
Not megapixels, pixels.
Pixels, yep.
Pixels.
Yep.
And if I have time at some point here, if we don't run out of time, I could pull up an old image from that camera. But what happened was, during that time, starting 25 years ago when I bought my telescope, light pollution got worse and worse and worse. And I finally gave up. My hat's off to you to still be an eyepiece guy unless you have a really big scope, because observing with an eyepiece I'm in suburban Metro Detroit in Rochester Hills. It's very light polluted here, and it just wasn't worth it anymore. There wasn't anything to see. That I could see the Ring Nebula. It was this pale disk that you could see was there, and that was about it. So I gave it up for 20 years. And then I bought a digital camera, just a photographic camera, and tried imaging with that, and realized that with some processing, you can cut through a lot of that light pollution. That image that I showed, let's see here, is it this one? Well, here's one I haven't shown, but here is a very faint galaxy. This was shot with my regular photographic camera stuck on my telescope on a fairly good night. I'm not even sure I could have seen that in the eyepiece. But with the extra sensitivity of the camera and with some processing that removes all the background, you can get images that are pretty satisfying. And there's another one, let's see here, do I still have it up? I do not. But if you remember the Dumbbell Nebula I showed, that big bubble, I'm very happy with that image. And that was done from my driveway on a fairly decent night. And that brought astronomy back to life for me. But it might be dying again, because now we have all these satellites up that go streaking across my images.
That is an issue.
I have one image where I stacked maybe 20, 25 images together, and my software creates a rejection map where it shows me the pixels it didn't use. There are 5 satellite streaks through that image.
Oh, I was watching the sky one night a couple of months ago, and I counted 14 of of Elon Musk's satellites going from the southwest to the northeast within a period of an hour.
I play an interesting game when I go outside. If it's really clear outside, the game is look up and how long does it take to see a satellite? It's shorter than you think.
Yes, yeah. Yeah, and if you are looking at the sky, the satellites are the little dots that you might think are airplanes, except they're not blinking.
Yes, they don't blink. They don't have colored lights on them, and they move generally slower than airplanes, but not always.
Yeah.
And they move very steadily.
And a
those
lot
are
of them
satellites.
will be in circumpolar orbits. In other words, moving, in a north-south or south-north direction. Those are the most common because a satellite in a circumpolar orbit, of course, can, over a period of orbits, can cover the entire Earth. And because of the rotation of the Earth, of course. So those are, your spy satellites, some of your different types of communication satellites and such are in circumpolar orbits. Paul, we were scheduled here, you were scheduled from 4 to 5:30. And, given the quality of the sky,
And the quality of the sun.
and given the fact that the sun is not entertaining us, we probably should relinquish this channel to another presenter.
Okay, I see we have 4 watching at the moment. If before we go, if anybody has any questions that are just burning them up, type them in the chat and we can answer them. Other than that, we will bid a fond adieu. I don't see anything popping up. So yeah, and here come the clouds again. Actually, we can watch the sunset in the clouds.
Okay. Paul, it's been fun talking with you and jabbering about the sun.
Yeah, likewise, John.
And let's do it again.
How's that for timing? As the sun fades away, so do we.
All right. Well, we're going to fade out, folks. Continue with other events in the GLAC presentations. Please notice the survey at the top of the web page. Please fill out the survey. Please give us likes, if you will, and continue watching the events. And these events also are going to be posted. Many events are going to be posted on our YouTube channel. So
and we're interested in creative criticism. Anything we can do better.
Yeah, that's right. My skin's pretty thick.
Yeah.
This has been fun. This has been fun, folks. I hope you enjoyed it.
All righty.
Paul,
Take care.
See you soon.
Bye, everybody.